Welcome to SMSCP Level 3 Mechatronics System Project Presentation. I am Alex Kurgat. I'm Sash Muragi. I'm John Omono. We are from Dedan Kimathi University of Technology, working under the supervision of Professor Jean Bosco. Our project is the development of a virtual reality digital twin for our Festo 3 magazine distribution station using Siemens TIA Portal Unity 6 for VR integration. The goal is to create a digital twin, a digital replica that mirrors the physical station's behavior with an immersive environment for training and visualization. What makes this project unique is that the digital twin creates live data from PLC and provides full HMI control, that is start, stop, color selection, and reset. All these are communicating directly with the Siemens S71200 PLC. Combined in OpenXR and tracking, it creates a fully immersive experience. We had different primary roles to serve in the project. I primarily handled the hardware assembly, the electrical wiring, and also the CAD modeling the station. I was responsible for the PLC programming as well as the HMI development. I developed the initial digital twin and the interaction layer that connects to the PLC.
So I'm going to take you through the components of these three magazine sorting station. So first of all, we had the modules which are mounted on each of these on the aluminum plate. So we have at the back we have the three magazines, which consist of vertical chute leading down to the double pneumatic acting cylinders with magnetic read sensors at the extracted and extended part. We also have the wiring for the pneumatic cables and also the electrical cables. Over this side is the conveyor module with the motor driven belt. This is the motor and the motor assembly that drives the belt. At the front here is the light curtain sensor, which is a safety feature for the whole unit. Within this is the light tower, which now shows the state of function of the unit. All these are wired to the PLC, all digital inputs as the sensors and the actuators as the digital outputs. So on this other side we have the flow sensor, which is used to detect the change of pressure along the pneumatic lines. And here is the compressor which runs the pneumatic lines that actuate the double acting cylinders. And at the other end is the HMI, which is used for input.
So this is a recording of the actual station working without the digital twin part. So I will control the station from the HMI. So for example, I can select one red part, one silver part, and I can press that. And in case I breach the workspace, you can notice that the system will stop. But if I want it to continue, I will have to come and press start on the machine and the system will continue. That is one good red part. That is a rejected red part. And that is the one silver part that we need. And that's it. So this is now the actual demonstration of the digital twin. In front of me I have the virtual machine and also the HMI, which I can be able to interact with using my hands. So I will select one of each object, one red, one black, and one silver, and I can press start. So I am presuming that on the actual machine, the part has reached the end. So that is the second object, the black part. And it has reached the end. That next one, the PLC has identified it as red, which is not required in the silver magazine. And that final part is silver. Okay. So this is the PLC programming and the HMI development that I did. Our machine has three basic parts. We have the CPU 1200, which is the 1214C to be specific. It is the brains of the entire machine. We have the ET200, which we used to increase the number of inputs and outputs that we have. And we have the HMI TP700 Comfort, which is used to place orders and also interact with the machine. Under the PLC, uh, we have three we have three main blocks. We have the main OB, the organizational block. We have two function blocks, and we have two data blocks. Under the main OB, we are calling both the physical and the virtual function blocks, that is these two. The first function block is used to perform the actual digital twin, while the other function block is used to create a simulated environment for training people on how to operate the machine basically without having the physical machine. So under the first function block, we have 9 main networks. The first network, it is used to read and write data to the data blocks, which are then read by Unity. So as you can see, for example, the first one, we are reading input byte 10, and we're writing it to data block 20 under byte 0. So it's the same for output bytes and then for the memory tags as well. In the second network, we are basically controlling the power that controls the entire station as well as the tower light. We'll have a look at that later. We also have under network 3 we have the selection and reset. So basically we are having counters, different counters. We have that one, and for the silver. And we also have the reset function to reset the entire station. Then we have the next three main networks are used to control the logic when a part is selected. So for example, the first one, when the red part is selected, this is the logic that runs it. I will also have a look at how that works. The seventh network, we have the logic that runs the conveyor. Basically, it runs the conveyor both in forward and reverse, and it is determined by the red, black, and silver networks that we have seen previously. And the final two, this is to help Unity recognize what is happening within the system. So the first one is used to spawn or instantiate objects. So basically when you place a part in the station, it will do the same in Unity. And as well as if you remove a part from the physical station, it should also remove the same part in Unity. The second function block is similar to the first one, to the first function block, that is the physical function block, only that for now it is disabled because we will be running the actual digital twin. But when the station is needed to train people or train students, then the second function block can be activated. So the virtual function block works in conjunction with this data block that contains the simulated input. So currently you can see all the values are false because we do not have it connected to the virtual station. But the second data block, this is connected to the actual station, and as you can see it already has values because the station is currently on. So that is it for the PLC. But also under the tags, we have these are memory tags, we have its input tags, and we have its output tags. For the HMI, basically we are using one main screen that contains the following. We have the start button, the stop button, the reset. The red, black, and silver is to select the quantity for each that you desire, as well as it will display the number. So let me just do a quick demo of the HMI. So this is the actual HMI in the station. So for example, if I press red, black, and silver, the actual station will move. You can press stop, you do reset, and that is it. As well as in the code, so in the code, the part controlled by the HMI is the part for selection and reset. So for example, if I press one red, you can see the counter has incremented. If I press one black, the counter, and that one is for silver. If I press reset, that is the block that is being actuated. If I press start, that is the part that is being actuated, and if I press stop, it is resetting the power. So okay, I will show a brief working of this power entire and the tower light logic, as well as the part, the red, black, and silver networks. So let me bring into view. Okay, so that is the physical station. So for example, if I press start on the HMI, you can see that the green light is on. But if I activate the curtain sensor, you notice that the red light is flashing, as well as on my code. Now if I actuate, if I select a red part and I press start, you can see that the red part is on. So that is a bad part. So that is a good part. So next I will show you the working of the tower light as well as the power. So for example, if I press start on my system, let me just press reset stop. So now I will show you the working of the power and tower light as well as the functioning of the station. So for example, if I press start, you can see that the power block is actuated as well as the green light is on. But if I disrupt the curtain sensor, you can see that the red light is flashing on my code as well as the actual station. And if I select, let us start with red. So this code will move pretty fast, so you may not be able to see everything that is happening. So let me press start. So you can see how the code, the lines are being actuated. So the first part is already out. And the second part is already out. Yes, thank you.
So my side of the project was everything you see in Unity. The communication with the PLC, the logic that drives animation, the HMI and the VR setup. The core of the whole system is this Unity game object, the PLC controller. It has a script I wrote that is called Simple PLC Mapper, and this is what talks to the physical PLC. If I open the script, you can see it uses an open source library called s7.net to establish a TCP connection on port 102 to the Siemens S7 1200. The IP is configurable in the inspector, defaulting to 192.168.10.1. So the way the communication works is it's a bulk read that every 100 milliseconds the script reads 18 bytes from the data block 20 on the PLC. Those 18 bytes contain everything. The first 4 bytes are the raw IO states. So the input bytes I10 and I12 carry all the sensor data, and the output bytes Q4 and Q6 carry the actuator states. Then byte 4 has the spawn and destroy flags, and after that we have byte 6 through 17, which are integer fields for type selected, current color, previous type, and 3 counters for black, red, and silver. So the integers are big endians, so the script handles the byte swapping. It also reads 2 additional memory bytes, which are MB100 for the control flags like start and stop, and MB111 for the reset flags. So that is the read side. Now, the question is, once you have those bytes, how do you turn them into 3D animations? So This is where the visual scripting graphs come in. I have 38 of them, and they all fall into 3 categories. The first category is the PLC readers. Take this red pusher control graph as an example. On every frame, it reads the extended cylinder R boolean from the simple PLC mapper. If it is true, it calls move with forward on the pusher controller component, and as you can see, the pusher controller here in the inspector, the positions are already defined. The script also uses move forward for smooth interpolation, so the virtual cylinder move at a controlled speed. The same pattern then drives the black pusher, the silver pusher, and the stopper. For the light towers, which work similarly, the graph reads the green light, the orange light, and the red light booleans, and then swaps the material on each lamp between a default material and a glowing emissive material. The second category we have is the sensor triggers. These are virtual equivalent of the physical sensors on the station. Each sensor is a trigger collider positioned exactly where the real sensor sits. When a workpiece enters the collider, the graph fires on trigger enter, grabs a simple PLC mapper reference, and calls write input with the sensor name and true. When the workpiece leaves, on trigger exit writes false. So for example, this sensor, its graph checks the material color of the workpiece that entered, and based on that, it writes 3 values back: workpiece detected, workpiece not black, and workpiece silver. That is how the virtual system replicates the 3 optical color sensors. So the third category is the HMI buttons. The HMI panel is a canvas that exists physically in the 3D scene, that rather than having a screen overlay, each button has a graph that fires on pointer down to write true and on pointer up to write false. So they behave like momentary push buttons, same as the physical HMI. The start button writes to the PLC address M100 bit 0, stop writes to M100 bit 1, and the color selection and reset buttons write to the MB111. The counter displays are text mesh pro elements that are trigger integers that the simple PLC mapper script updates with every frame. For the workpiece simulation, when the PLC signals a spawn, one of the spawn graphs instantiates a prefab. Each color has its own prefab. So the graph adds it to a tracking list, and a separate script handles the two-phase movement. First, it follows the pusher towards the chute, then it switches to conveyor style translation. So when the PLC signal destroys, a track graph removes the first item from the list. Then we have the VR layer, where we have the XR rig, which uses the OpenXR and the XR interaction toolkit, which has the XR hands for hand tracking. The setup has a tracked camera, left and right hand controllers, and a locomotion provider for vertical movement. Because it is OpenXR, it targets the MetaQuest, but it is not locked to that specific headset. In VR, you can walk around the station at full scale and interact with HMI buttons using your hands. The same canvas that we use the mouse click also responds to the XR poke interactions.